Hello, we are back. Logic for computer science, classical and non-classical. The lectures for 2 logic courses, 1 graduate course, and 1 mathematics and computer science undergraduate course. And here we are. And here's the book, and here is Anita Wasilewska. I'm the author, and here we are. So now we do the chapter 5, which is Hilbert proof systems, completeness for classical propositional logic. It's a lot of slides. I'm not going through all of them, but I'm going to comment where it is really needed, and we're going to cover all essential parts, and the slides are there. So we divided the chapter in 5 sets. So first we do Hilbert proof systems and proof system H1, and we will do the proof of deduction theorem, which is a very essential logic theorem without which we cannot carry the proofs of completeness theorem. And then we move to a more complex proof system for which we will be able to prove completeness theorem, and that is part 4. And then there is 2 proofs of completeness theorem. We are going to cover the first, and the second I will just comment on it later, and then we'll cover some other axiomatization, because we only bring 2 proof systems which are sort of, in a sense, minimal to other existing proof systems. Okay, so now we have a proof system H1. So these are called Hilbert proof systems. In general, proof systems which are called Hilbert proof systems are based on a language are based usually on the language with implication and contain modus ponens as a rule of inference. Modus ponens is probably the oldest and best known rules of inference, known in 3rd century before Jesus Christ, and it's also considered the most natural and intuitive thinking, and the proof systems containing modus ponens are special proof systems. And of course, this kind of proof system, which contain that rule, put major emphasis on logical axioms, keeping rules of inference to minimum. Often admitting, especially in propositional case, modus ponens as the sole rule of inference. And so we will do first the classical propositional logic and discuss how the techniques can be extended to predicate logic for non-classical logic. The first proof is based on the one included in Elliot Mendelssohn's book, Introduction to Mathematical Logic. Easy to Google. It's a very, very, very classic book. Pretty dense, so that's why I wrote my book. So it is constructive proof and shows how one can use the assumption that formula is a tautology in order to construct, in a sense, a formal proof. And second is not constructive. The importance of the second proof lays in the fact that the methods it uses can be applied to the proof of completeness theorem for classical predicate logic, and it is presented in chapter 9, and also it generalizes in complex ways or less complex ways to some non-classical logic. So this is a very powerful, much more powerful technique than the technique used for the proof 1, which is really only for classical propositional logic. So we proved completeness part of completeness theorem for the proof 2. Wait. The second proof is non-constructive. Importance lies that we can that it can be extended. And the second proof, we prove the completeness part of completeness theorem by proving converse implication to it. It means we show how one can deduce that a formula is not a tautology from the fact that it does not have a proof. So that is called a counter-model construction proof. And of course, the construction is not constructive in the sense of the first proof. And also both proof rely on deduction theorem, and so this theorem is the first we are going to prove. So now we define a Hilbert proof system H1, and based on a language with implication only. So this is a very, very one connective language. And we have modus ponens and the sole rules of inference. And here is the Hilbert proof system. Language is with implication only. You have two axioms. You can see they have special names. They are special axioms and modus ponens. I'm going to write now those axioms on the board because to explain things, we will be using them. So we have axiom A1, which is A implies B implies A. And of course, A, B are any formulas, so can be as complex as you can have. And the other is A implies B implies A. And you have modus ponens rule, which says if we have A implies B, we can deduce B. And again, A and B are any formulas, so this A can be totally different than that B is different than that. That means any formula. We just use A and B because the first letter of alphabet, but this A is not exactly this A, they are any formulas. So here is our system which we have, and formal proof. This is a beautiful formal proof of A implies A, which is the basic tautology, A implies A. And here is formal proof. And you can see that here's the proof. You start with axiom 2, which you take this axiom 2 for A in the axiom equal A, and B in the axiom equal A implies A, and C, of course, I wrote axiom 2 twice. So axiom 2, you see, you always find where you made the mistake. So here's axiom 2 is A implies B implies C, and implies A implies B, and now we need then A implies C, and then we need the proper parentheses. Here you have 3 parentheses to close the formula, and modus ponens is A implies B, so I'm not going to keep it all the time. So we have 2 axioms, and now to construct the proof, you see, that's how I found that we take axiom 2, this axiom, for a certain A, so the A is just A in B1, and B in the axiom, this B in the axiom becomes a formula. Here we take this B, we take a formula A implies A, and this C in the axiom, I take A, and I take A being A, and so this is called a substitution of, we substitution of particular case of that axiom as B1 of the proof. Wait, because I have a lot of now. All right, so that we already know. And the next thing, so you can see that inventing even starting point is pretty complex, but how we do it? We know that we have modus ponens. When you think about modus ponens as the rule of inference, you can have that you have A, and you have A implies B, and it means you can cut A and deduce B. So this is in a proof if you have A, and then in a proof you have A implies B, you can, by modus ponens, cut this A and deduce B. So that's why also modus ponens is called a cut rule. So when you look here, my goal is to cut by modus ponens whatever I have, that's why I put it in red, to at the end get only A implies A. So here I have an axiom. Now, and you can see the main connective is implication. So when you look at this, that is axiom A1, a particular case, axiom for B, this B equal A implies A. So now I can cut from B1, B2, I can cut that part, and I have only this part left, and this is our B3. And now when you look at this, my goal is to get A implies A in red. So now, I have this. Can I cut this? I can put axiom A1. When you look at this, it is a particular case for B equal A. You would get A implies A. So that is a particular case of axiom A1, and I cut it again, and I have a proof. So this is pretty, it's a nice proof. Usually, and I will show you much more of the proofs as to, first of all, how it works, but also, usually in logic books, that's the only proof you get. So we'll have a lot of them. And of course, we have a fact that we proved A implies A. A implies A. And it's not that obvious how you do it, not mention that we talk about syntactically decidable system, with a system where the inverse rules could be reversed. That proof, it's just impossible to automatically reverse. So, and then I bring back, often in my slides, when you read the slides, I bring back the previous definitions to make all lectures self-contained. So I brought back definition of syntactically decidable and undecidable, so everything is there. I'm not going to repeat it, but Hilbert proof system, because of modus ponens, are never syntactically decidable. And it, explain, you can see it nicely. So any modus ponens, when you think about it, what's happening, if you will have a modus ponens, you have A implies B, and you deduce B. And now if you want to reverse and say, okay, how did I deduce B by modus ponens? It means I had A and I had A and B. A can be any formula, so there is infinitely many of such formulas, so you cannot have finite procedure of finding it. So that's why you really need to use very heavily your mind how to find those steps in the proof. And now we have semantic links. That system H1 is obviously sound under classical semantics, because you have this are tautologies, this are tautologies, this is a sound rule. So you have soundness theorem for this system. It means that if formula has a proof, then it is a tautology. And also, it's not complete. Remember, our goal is to prove completeness theorem. So now, why it is not complete? We have a very, very simple proof system, and we did it in purpose, because also it's nice to see how much we can do. And so completeness is H1 has a proof if and only if is a tautology. So all tautologies must have a proof. But our language contains only implication, and for example, you have a tautology, what I gave you here, not A implies A. It is one of basic tautologies, but you cannot, it has negation. You can't define negation. This negation is not in the language in terms of implication alone. So and that's we proved before. So you cannot have all tautologies, because even not all tautologies can be expressed in that language. Now there is next notion of a proof, which we did cover, is a proof which uses a certain extra information, which is called hypothesis. So the next notion of a proof, which we will be heavily using, is to find a proof, to define a proof of formula in our system, whatever H1 or system S, from gamma is a set of formulas. So that is called the proof from hypothesis. So roughly speaking, and here is the definition, I repeat it, roughly speaking, you have the formal proof is just a proof, but what we now have is you have a proof, and you can, at each step of the proof, you can use logical axioms or that formulas from that gamma. So that's why hypothesis is the name we use it, but you have like helpers, and then everything is the same. So and that is very so for example, and this is, for example, let's construct a formal proof of A implies C. I want to, from A implies B and B implies C. It means I have it. I proved it already, or I called it by hypothesis. I want to see if I can prove A implies C using those hypotheses. So it means in the formal proof, you can write a logical axiom. That's I write, but also you can write also hypothesis. So hypothesis, that an extra information. So we have information that I have B implies C, I have A implies B, and I have axiom. Now I can add axiom A1 in that form, and because I have, you see, I have already B implies C, so I can cut it. So I get this, A implies B, and now I can write modus ponens by modus ponens, I have A implies B, and I have I can apply the modus ponens to this and to what I already have, and I get A implies B and A implies C, and I have already A implies B as hypothesis. I use modus ponens, and I get A implies C. So, the fact that we can do it and is called deduction theorem. And deduction theorem, which I'm going to prove, means that if I have a proof using some formulas and A, and I get B, that happens if and only if you see this A is the same as implication A implies B. In particular, when gamma is empty, we says that if A implies B, I can prove from A in a system B, if and only if I can prove A implies B. Here, gamma empty means that you have only logical axioms. So this is like normal logical from logical axiom. So you can see if you have to prove implication from the logical axioms, you can just put the N A as a hypothesis, and that makes the proving easier. So that is, and we do, let's use the deduction theorem to prove that fact. That is a fact which we will be using in our Hilbert type proofs a lot. So for example, one is that A implies B, B implies C. In H1, I can prove from this, you see you can cut this B and prove A implies C. And here that means that from A, B, C, I can prove B, A, C. It means I can exchange B with A. And of course, by deduction theorem, if we have deduction theorem, A can be written, you see, A is here, so I can put the A here. So that is an easy proof, and I'm going to prove this. How you construct a proof from A, B, B, C, A, proof of C. It means I have this is my hypothesis. I have this is my hypothesis. And I have A, because it went by deduction theorem to the set of hypotheses. I have A. And now you see this A with this B1 with this, you can cut this A here and get B. And now I have already proved B, and I already have B implies C. I can cut this B, so I have C, end of the proof. So you can see it makes proofs very pleasant. And okay, so that's another proof. It's a little bit more complex if you want to prove A, B, C. This is lemma B. I also change that B from here goes here, and I take this as hypothesis. I have B, so and also I have axiom A because I want to cut this B. So I have axiom A. I cut this B, so I have A implies B, and now I have now I can write the axiom 2, and I already got this by B1 and B5, so I can cut this, and I have A implies C, and by deduction theorem, I proved what I wanted to prove. So, of course, you can, deduction theorem, we can get an easier proof. It means that if we can prove that I want to prove this, I can apply deduction theorem twice. It means I can put B on the left side, and then I have this, and now I apply deduction theorem again, and I put A on the side. So proving this is the same as proving that. And proving this is, look how absolutely proving this is a trivial, because I have this as hypothesis. I have B, I have A, and now I can cut this A and that cuts, so I have B implies C. Now I have B, this B cuts with that B, I have C, end of the proof. So that is advertisement for the beauty of deduction theorem. And now we want to prove it. So this is deduction theorem was proved by Hilbert in 1930. And so it's a very, that was the time when people were working on completeness theorem of propositional predicate logic and so on. So that's, and then I repeated it here. So this is an original Hilbert that you can only do one, and then you can add any other set of hypotheses. So the same works for any other set of hypotheses. And we want to prove, and that's now, we want to prove first the if part. So it means we want to prove if we have gamma A proves B, then from gamma I can have a proof A implies B. So assume that it means that we have a proof. So now I am going to write, okay, so let's now see. Our assumption is that we have assume that gamma A proves, I skip H1 because I have fixed the system, so I don't need to write it, proves B, and I want to prove, that gamma proves A implies B. So, and I will show that this is my information, and then I will construct proof of A implies B. Because it's constructed, it means I will give you a method how to get that proof. So what does it mean? We have information that gamma A proves B. It means you have B1, B2, Bn. This is my proof. I have it. I have this proof from the set gamma A. And we want to show that. How to find or construct from that information that proof. Now, that's again what happens very often in mathematics. We prove a little bit stronger statement. It means that in order to prove this, we will prove that gamma proves A implies B I. This here is somewhere BI for all I equal 1. And so it's a stronger statement that the gamma would prove A implies B1, A implies B2, etc. In particular case, the last case would be Bn. You see, you know that Bn is B by the definition of the proof. So at the end, it would prove Bn. So we are going to do this, and of course, we are going to do by mathematical induction. So this is a nice application of mathematical induction on the length of the proof. So first of all, if you do mathematical induction over I, base is I equal 1, and then you go from I to I plus 1. So what happens that the I equal 1, it means that B1 is logical axiom or is in gamma. or, so that is here, or B1 is A because is or in gamma or is also A. So this is our inductive, we have that the base case is this. So let's see if it's true. So what does it mean? B1 is logical axiom. So B1 belongs to is logical axiom 1 or logical axiom 2, or is in our gamma, which is non-empty set. Or empty, can be empty, it doesn't matter. It's any set of formulas. Now, what we have, we know this, but we have an axiom. We have that we can write axiom 1, we can write as B1, A implies B1. So this is a substitution of axiom 1. And we know that B1 is one axiom or the other. So the proof from gamma would be I have B1 because I have an axiom, and I have this has a proof because it's substitution of the axiom. So I have this, A implies B1, and I apply modus ponens, and B is cut, and I have A implies B1. I had a proof of for I equal 1, I constructed a proof of A implies B1. And the case 2, when B1 is A. So what does it mean? B1, and I want the thesis is now, if B1 is A, I need to prove that gamma proves A implies A, right? Because B1 is A, but we know that I have a proof of A implies A. That was our proof we did in full-fledged proof of A implies A. So I know that we already have this proof. So this is already proved. And by monotonicity of the consequence, we also have that gamma proof all this. So in this case, we have that gamma proves A implies B1 for this case. In both cases, we prove that gamma. Here, you see we prove this, and the fact that we can put gamma comes from monotonicity of the consequence, classical consequence operation. So we prove the base case. And now I just want to assume that gamma proves A bk, some k in the sequence, and we show where for all k less than I. So we use what's called the strong induction. So we assume strong induction. We assume that gamma proves A implies bk for all k less than I. This is our, and want to prove that gamma proves A implies Bi, the formula for. So this is now our proof is we assume that gamma proofs A implies bk for all k less than I, and I want to prove, and by induction you have that it is for all I. So now we have assumption, and let's see what we have. Again, you have two cases. Our bi is like before, axiom or gamma or A, and or case 2, bi follows by modus ponens. Now let's see what's happening. Case 2, case first is identical. So what does it mean that bi, which I want to prove, this bi follows from modus ponens from some bj bm where j is less than I and m is less than I and by mathematical induction they both are already proved. So now we have this situation that bi is conclusion by modus ponens. So by the definition of formal proof, we have bj bm where j is less than I, m is less than I, right? Such that, and of course they are different, j is not m, that you have bj bm, you have modus ponens, you get bi by modus ponens. But you get it by modus ponens, what does it mean? And here is the key. What does it mean that bj and bm, this is modus ponens. So it means that modus ponens is A implies B. So it means this bm must be A would be bj implies this b was bm bi. So that must be bj and bm must be of that form because that's the form of modus ponens. So I know that by modus bj is you got from that. But now, and by inductive assumption, so it means bm must be of that form. So and we know that j is less than I, so by inductive assumption, this has a proof. So I know that by inductive assumption, we have that A implies B, J implies BI. It always happens for I and J less than M. So now we have the beautiful substitution of the axiom 2, so which has a proof because you can always put axiom in your proof. So by monotonicity of consequence, you can put gamma in front, and now it means that I have this and I have this. I can cut these pieces and I have the proof A implies Bj implies A implies Bi. By monotonicity, I can put gamma in front, and again you can apply modus ponens because I have a proof of that. I can cut this and I have proof of gamma. A implies Bi, it ends the proof of inductive step. So the inductive step ends the proof because it means that's for all I, and in particular case, so you have that it happens in particular case for Bn equal B. So we prove gamma implies A and B, and so that is the first part of deduction, and that also gives you how to construct that proof. And the other side is pretty, the inverse implication is pretty obvious. Assume that A implies B. Gamma proves A implies B. By monotonicity, I can put A on the side because that set is larger than that. And now I have A, obviously, gamma A proves A always, and I can cut the A, and I have the proof of B, so I have that part. So this is pretty obvious. So we prove that deduction theorem. Now we go to, we proved that our little system H1 was not complete. So now we extend the axioms of H1 to a little bit larger system, which we add. So I have now, we add one more. First of all, now we have a system which we keep the axioms of H1, but also H2, first language has implication and negation. So we extend the language, we add implication to the language. The whole not completeness of system H1 followed from the fact that we couldn't define negation in terms of implication alone. Now we have now two connectives. I have implication and I add negation, and from the finability of classical connectives, we know that that language is equivalent to a full language of classical logic, because all other connectives can be defined in terms of implication negation. So we can think about this language. This is like minimal language for the whole propositional classical logic, and we prove that we can do it. Not totally minimal. I will show you that we can. We also know we can have only one connective, but it's not implication, and so on. But once you have implication, and we need to have implication because we sit in Hilbert style with modus ponens. So now our language is richer. So we cannot say that, oh, I cannot prove. You cannot prove some formula. It doesn't mean that you cannot prove all tautology. You cannot have the same argument as we had for H1. So now we keep those two axioms as we did, but now the formulas, this A, B, and C, are from richer language. But you see when, and then we add one. This is nice. Like minimal axioms, set of axioms, we add one axiom, we talk something about the implication. So we add an axiom which talks a lot about the implication. It means we add A3, which is not B implies not A, implies not B implies A, implies B, and now I close the this, I close this, I close this, I have a proper, and you have, so we add one axiom. Of course, we get H2 adding one axiom. In H2, the deduction theorem use axiom A1, A2. It didn't use negation at all, so it's independent. The proof is independent of the connective negation, so we have deduction theorem for H2. So now we have deduction theorem for H2 in obvious way. And now, of course, H2 is sound. under classical semantics. This is one of our basic tautologies. So we have a soundness theorem. So we have to prove, our goal is to prove the completeness theorem. And we are going now to carry the proof of completeness theorem. But before, I will show you some examples of proofs in H2. All right, so now we prove the completeness theorem. We know that the proof of completeness theorem for a given semantics is always main point of creation on new logic, and there are many techniques again to prove. And we will present two proofs of completeness, but really I will talk to you only about the first proof for system H2. So now our system H2 will prove that it's a complete proof system for classical propositional logic. But before, I want to show you some examples. Okay, so I'm not going to show now all of them, but at least one. So what I want I treat it for you as a training ground to learn how to develop those formal proofs. You could see from the first proof, there is like different ways to think how you do it. You have to do it with a lot of thinking in your head. And like in any thinking, there are some patterns. So first of all, these are those two lemmas which we proved. A and B, and that's why I already proved them. Using the deduction theorem, we know that we have those lemmas for H2 because we proved that the deduction theorem holds for H2. So, for example, and then you have, here is consecutive steps which are proof. I say so. This you have first step, and this is a proof, not B implies B, one of the basic tautologies. I give you a proof. Now, your goal is to say why it is a proof. Yeah, it's like a proof is a sequence. What is this? Why it is a good step? What is this? Why this is a good step? What is this? Why it is a good step? And so on. But then you can see, for example, certain things already, that I have this, and if I have this and this, by the modus ponens, I can cut that, and I will get this part. And when I have this part, I have whatever I have. So I give you a lot of exercises which I show you how to fill those gaps. So here is the comments that completes the proof. For example, when you look at B1, that is axiom A3. And this is a substitution for A equal not B, etc. Now, B2 is lemma B. Lemma B is this. You see A, B, C, B, A, C, and this is application of this lemma, which we proved by deduction, using deduction theorem and constructing the proof for particular A, B, and C. So here I rewrote it that lemma B would be this, this, and this. And now what the lemma says that you can exchange this with that, so you have this, and you have that, and you have that B2. So this is a little bit difficult, but it's not that difficult. And then now I put this. This is not B implies B. This is a particular case of A implies A. So here is a fact we already proved. In particular, we can put the whole proof A implies A instead of it, and that is done. And now you have the modus ponens, which I explain. And now this is an axiom. And again, the next step is application of lemma A for the particular. I have this, and lemma A said that I have that. So that was quite difficult case. So, but I wanted to start with more sophisticated. So, and then there's one remark, right? I say that that formula is a particular case of A implies A. So if you want to construct a proof from the axioms, you can rewrite you can insert before this step, here in B3, you can insert the whole proof of not B implies B. So for example, I did it. You see, I have 1, 2, and now I insert of the proof of, I copied from A implies A for B and B. So here is the whole proof. You can insert the proof which already we had for A equal not B, and then you have an old B3 would be now B7, and then you carry the proof as it goes. So, and then I think here is an easy one case. Again, you have proof of B implies not B, and now you can like look, what is this? What is this? How I would get this? So, and again, I will give you nicely, even I wrote where how you apply modus ponens, and then how you apply lemma A. Those lemmas A and B are very important. And here you have example 4, example 5 with filling in the gaps. And I did it not only for you to get a training ground, how you do it, how you understand those proofs, how you fill that gaps, but also first of all, I didn't find in any of books none of those proofs. It was always like, oh, this is easy for the reader. It isn't that easy for the reader. But why we do it, that was a nice exercise. It was very simple. So I did 8 here. I did all those exercises. I constructed all proof of all those formulas. So now I show you how to construct the proofs in H2 of all those formulas. Why I did choose those formulas? They were not random choose. They were chosen, like for example, I need this for the proof of that and so on, but they were chosen because the formulas 1, 3, 4, 7, 9 from the set of probable formula are needed together with logical axiom of H2 to execute those 2 proofs of completeness theorem. So the completeness theorem uses already a previously proved tautologies. And of course, you can see which one you need for the proof 1 and which one you need for the proof 2. So that was very important to have a proof of everything we need for the proofs of completeness theorem. So now we do the proof of completeness theorem. So it is similar in structure to the proof of deduction theorem. Proof 1 is due to Kalmar, 1935. Deduction theorem was 1930. So you can see there was a lot of progress in between. And I present a detailed version of Elliot Mendelsohn book, Introduction to Mathematical Logic. I say detailed because you see usually when you have proofs in those books, they skip all details. That, oh, this, in five lines, there's the proof. but defined lines happen sometimes to be 3 pages. So I'm giving you all details, just to show you that everything can be reconstructed and also to make you understand better what's happening. So, and okay, so proof 1. And also, again, this is a good, important remark, that proof 1 is specific to that, and proof 2, to that particular language. Now, it can be extended to all other languages. We usually included the full language of classical propositional logic. So we do so by adding new special logical axiom to the logical axioms of the system. And then we prove whatever more because we need more information about those new logical connectives. So one can think about system H2 as like sort of minimal Hilbert proof system for classical propositional logic. Minimal in 2 because I will show you that you can have only one connective. And proof 1 cannot be extended to the classical predicate logic, neither to variety of non-classical logic. And of course, that is our H2. So of course, we have Soundness theorem, and we have all those, I repeated it, provable in H2, which we will be using. And so to do the proof, we need some definition and some notations. I'm going to write this definition on the blackboard because we will be using it. Okay, there's one more thing which I want to remind, that all the slides as I present and even more are attached to this presentation. So when you listen to my lecture, or you take your slides, or you study and you keep going, because that's how it is. And all slides are on the courses webpage and more. So notation. We have a certain definition. First, we write A, B1, Bn for B1, Bn are all variables which appear in the formula A. And now and this is Lemma definition, that giving a truth assignment which takes variables and Tf, we write two formulas, A prime, which is A, and A B1, Bn. A if V star A is true, so it means that that truth assignment evaluates formula A into true, and negation of A if V star of A is false. And you can see that that only happens in classical logic. And now we construct the formulas Bj, which again the same Bi and not Bi, where Bi is evaluated into T, and the same Vbi is evaluated T this is extension of V. V is on variables, and then V star is extension of that V from variables to the set of all formulas. So these are our special so for example, when you have a formula A implies B, so it has A and B, and you evaluate at variable assignment, you put A into T, B into F. So B1 is A, B2 is B, and you evaluate the value of the logical value of the formula would be T, so A prime T, so A prime equal A, and B1 is A, you see A, VA is T, so B1 is A, so VA is T, and B2 is not B because B was evaluated to F. And you have more examples. And now we have a main lemma. So that is very easy. If you want to do it fast, you can see fast. Let's do fast. You have a formula A, B, C. A implies not B implies C, for example. So what it would be, and I have V A equal T, V B equal T. I am lazy, so I have everything into T. So you evaluate, this is your formula. So A V of A, V star of A, would be T implies not T implies T, which would be T implies false, implies T. So T implies false is false, so it's F implies T, which is T. So you have that VA is T, so A prime equals A. And now B for A was T, so A would be our B, let's say BA, B, 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 C. BA would be, because A is T, so BA would be A, and here would be A, and here would be A. So in that particular case, for that V and that variable assignment and formula, you have, we evaluate quickly what is A prime and what is, which are those B, capital B cases. And main lemma says, now main lemma says that B1, B2, Bn proves A prime, you see? So when you have those B's, that gives you a proof of A prime. So in this case, the main lemma would says that A, this is BA, B1, this is B, sorry, I was B, B, C, B, C proves A prime, which is A. So the main lemma would say that I can have a proof of that formula, so that would say that I have a proof A, B, C proves my formula A. If you have the variable assignment, the truth assignment, it says that you can construct the proof from A, B, C of the given formula, which is A prime. In our case, A prime was A. So that would be, it's a very strong, beautiful lemma, which just shows you how you construct the proof. The lemma says there is a proof. So what does it mean there is a proof? And the proof, let's say, like proof C1, C2, Cn, this is your proof of that formula from A, B, and C. And N is the legs of the proof. And now we construct the proof by induction on the degree. So we do this proof by induction over degree of A. This formula has 1, 2, 3, right? Degree, so this formula is degree 1, 2, 3, because degree is the number connective in the formula. So base case is n equals 0. It means A is atomic, so consists only of a single propositional variable. And if VA of that variable is T, by Lemma definition, A prime equal A, and B1 is A, we obtain by the definition from the probability of the set gamma, we have that A proves A, which always happens because you can always prove A from A by writing just A, right? A proves always A proves A. It means this is your proof. That's it, because that belongs to gamma equal A. So we have a base case. Now, if F, because you have everything depends on V, so our V can be T, or V now can be F. So if V is F, we have A prime is negation of A. So it means A was one variable, so would be negation of A, and B would be also negation of A. A by definition of probability, you have A dot A proofs on A, and so we have the main lemma for n equals 0. An inductive step, we assume that main lemma holds for any formula as we do the strong induction, J less than n connective, and now we prove the main lemma holds for n connectives. J less than n, we prove for n. And we have subcases, not that many, because remember the language, our language was negation implication. So we have main connective can be negation or implication. So main connectives, you have two cases, implication and negation. So first case is A equal negation A1, and we assume this is negation. So degree of A1 is less than n, because it's less. So by inductive assumption, we know that we can have that A1, B1, we have the A1, B1, Bn corresponding to that A1, that lemma says that B1, Bn proves A1 prime by inductive assumption because A1 is the less degree that our A. Now, depending on our V, right? Now, remark, because remember those Bn, we assume that A has all variables are B1, Bn, and these are corresponding to these variables. So if you have A1 has variables b1, bn, so negation of A equal negation of this has the same variables, so the variables are exactly the same. So this is important. So I say that, so we have the same capital B's in both formulas on A and phi, and now again we are going to show that inductive assumption allows us to prove that that would be, because inductive assumption is for A prime, right? We have A prime is by inductive assumption, and I want to prove that the same thing would hold for our formula A. So again, we have two cases. Our VA1 is true. So by Lemma definition, for A1 prime is A1. By inductive assumption, all these B's, depending on our V, are proofs A1. So in this case, V of A, our A, remember, is not A1. So V of A equals V star of negation of A1. And we have the case that VA1 equal T. So the V would be F, right? So now, so we have that A prime for our A would be negation of A, because V of A was F, so that would be double negation of A1, which was, so we get, now, we know by, so we know here, okay, I want to bring this. I have that A prime equals not A1 in our, and I want to prove, and I want to prove that B1, Bn proves A prime, right? This is goal. But what I know, Lemma, we already proved that A1 proves not A1. In our H2. So we know that we have a proof of that. Inductive assumption, by inductive assumption, you have B1, Bn proof A prime. If we have the proof of this by monotonicity, I have that also B1, Bn, which are the same, prove this. And now I have this and inductive assumption. So here inductive assumption, okay. Inductive assumption was that B1, Bn prove A1. So that was our inductive assumption, was that B1, Bn prove A1. And now, and I have that formula, so I can cut this and this. I have the proof of A1, and I have proof of A1 implies dot A. So now from this and this, I have that B1, Bn prove that not A1, but not A1 was equal A, not A was A prime was the negation of A, which was double negation of A1. So we get that B1, Bn proof negation of A, which is A prime, end of the proof in this case. And the same for F. In F, we have that A1 prime is negation of A1. So VA is true, so A prime is A. And by inductive assumption, we have B1 Bn is negation of A1. And as A prime is negation of A1, you have B1 Bn proves A prime. Now, with implication, it's a little bit more complex. But first of all, with the implication, A, you have implication are two formulas, and you know, but inductive assumption holds for A1 and A2. But A1 has certain variables, I don't know which one, and A2 has also certain variables. Some of them are the same. So, and A1 and A2 have a less connective, so I know that C1 CK proves A1 prime, and D1 Dn proves A2 prime. And they are subsequences of those Bn capital B's, which are for the formula A. So I can always say, because those B's are like union of all of them, but by the monotonicity, I can extend those C's to all the B's, and so D's to all the B's. So now we have that I have cases that if A1 evaluate both of them in T, so if A1 evaluates in T, so A1 prime is A1, and the same A2 in T, so A2 prime is A2. So we evaluate A1 implication T, because they are both T, would be T. So A prime is just the implication. By inductive assumption, you have that the B's by monotonicity proves A2. Now we have axiom 2 and monotonicity, because I want to cut this A2. You see, A would be A1 and 2. So I want to cut this A2, but I have axiom 1, which I can write as A2, A1, A2, and I cut A2, and I get that B1, Bn proves A1, A2, which was our A prime. So that was easy. And now with where truth and false, we get that A1, A2, it means A, VA is F. So A prime would be negation of this. And now I have lemma, monotonicity. I have such a formula, which I proved already. That's what I needed to prove it, that A1, and I would cut this. Now, because A1, you see, A1 prime is A1. A2 prime is A2. So by lemma 7, I have this. So now I have A1 prime is A1, so I can cut this. And I get the proof of that. I cut by A1, I cut this piece. So I get A2 implies negation A1, A2. But I have also, by inductive assumption, I have a proof of negation A2. So I cut A2, and I get the proof of negation of A1, A2, which is A prime, and end of the proof in a case, in this case. And now, when I have, now implication, just to remind them, implication is our classical implication. So I have T, F, T, F, F, T, T, T. So you can see if A, and you have A1 implies A2, if A1 is F, A1 is F, A2 is always true. So if A1 is F, A prime is negation of A1, and V always gives the true, so A prime is A1 implies the A2, so I get from this that B1, Bn proves negation of A1, and again, you have formula 4 that we prove that not A. You see, I have by negation, you see, here's our inductive assumption. I can cut this, and what I get my A prime, which is A1 implies A2. So by modus ponens, I have proof end of the main lemma. Now, I'm almost done. So, proof of completeness theorem. So, completeness theorem says it's completeness part if tautology then has a proof. Now, it means that assume that A is tautology, and I show you how to use this lemma to construct the proof. So it's tautology, and let those B's be all variables in A. By main lemma, I have A is a tautology. I have that assume A is a tautology. By main lemma, for any V, we have B1, Bn proves A prime, right? But A prime is now, A prime is always A for any V. So I would give that B1, Bn proves A proofs for any V, we have to prove that B1, Bn proves A. Now, this V takes variable and TF, right? And A, those capital B's are corresponding to little b's which are in our formula N. Now, I know that A prime equal A for all V, because A was a tautology. So now, what's happening on those little b's? Those big b's depend on V. So first, I have take V such that I start here. B, V, Bn equal true. And another case, V, Bn equal false. So you have any variable assignment on that variable B in our formula A can be true or false. So what happens here? We get, in this case, we have that B1, Bn minus 1, Bn proves A, because Bn equal Bn. And in this case, you have B1, Bn. Bn is F, so Bn minus 1. Bn would be negation of Bn proves A. So I know by inductive assumption that I have this main lemma. I have that this must hold and that must hold. By deduction theorem, I have B1, Bn minus 1 proves Bn A. And the same deduction theorem here, I get B1, Bn minus 1 proves in our system not Bn implies A. So I have that by deduction theorem, I have those two things. But now I have a magic formula which says A implies B, then not A implies B, implies B. By monotonicity, I can add those capital B's in front of that. But A implies B, if you take this A equals Bn, so the lemma 8 would be, if you take this A is Bn, and negation of A is not Bn, and this B is A, I have the proof of that. I have it, I constructed, you see. This proof we constructed from scratch. So I have that I can construct this proof. And now you apply modus ponens. You have this, and you have that. So you apply modus ponens once, modus ponens 2, and you get proof of A. So, and the same if you have the case where now we look at Bn minus 1. Now when we look at B minus 1, what does it mean? You repeat the same, that the value of Bn minus 1 can be true or a capital Bn. So now the value of, you can have V of Bn minus 1 can be true as here, or V of Bn minus 1 can be false, the same cases, and we apply exactly the same. So now you have Bn minus 1, here Bn minus 2, and here minus 1, and here you have minus 2, and then you have Bn minus 1, and you apply, and you eliminate Bn minus 1, and you keep eliminated that you finally get a proof of A. And we constructed the proof of A for any V. So if A is a tautology, we have a formula how to construct the proof of A. Very nice proof. Now, and that is constructiveness proof, because again, all lemmas, all the formulas, we constructed the proofs. So the deduction theorem, which we did use, also had a constructive proof. So everything, we can reconstruct the proof from axioms from the very, very scratch. A lot of work, but it can be done. Now, I want, and there is an example which, more complex than I did on the blackboard, and you have elimination step by step, very beautiful, so you can see more examples than we did it here on the blackboard. So first exercise, the lemma formulas, we said they were needed in completeness proof for both theorem. List all the formulas from lemma 1, which I really listed you, that are needed to prove 1 alone. And again, and that is important, that system H2 was obtained, and the proof 1 was for the language only with negation and implication. We can now extend the language, we can extend system H2 to H3 to the language which, for example, contains disjunction. So adding new cases concerning axioms which would concern the disjunction. List all new formulas needed as new axioms to H2 to be able, and also formulas we need to prove, to follow the proof, to follow the methods in original proof 1, and then extend it to all, even the full language of propositional logic. So proof 2, I am, okay, I'm not going to go through this, but because the proof 2, exactly the structure of this proof will repeat in the proof of predicate of completeness of classical predicate logic. So it's exactly in more complex case, but so I will repeat this proof when we do the predicate logic. But I just want to show you how here first how complex is consistent, inconsistent cases, how complexity of that proof and constructions are very, very, very complex. That's why, so it's worth to look at it. But it's really beautiful proof, especially with the set sigma, that is delta star, which is the extension to the complete set delta, and so on. And you have made lemma, and then you have proof of completeness theorem, which is exactly what we do in predicate case. And that, and you have those infinite sets. That construction can be extended to more complex logics, or of course with some changes, but the technique can be extended. So I want to end. You see, it's still going on. Really beautiful proof. You have it. Now, I want to end to mention some other axiomatizations, because we use that nice axiomatization. Why? Because, you know, when you have only two connectives, you have less axioms and you have less inductive cases in the proof to consider. If you add more connectives, you need more axioms for those connectives. So that's why I gave you exercises which says, take this proof, add axioms you need for disjunction to be able to carry exactly the proof I gave you. Good exercise, because in this way also you understand better the proof and the structure and what the proof is about. So, and here are some classic axiomatizations of classical complete axiomatization. Those people prove that there are completeness theorems for these axiomatization. Łukasiewicz, which was 29, and we had Łukasiewicz three-valued logic. We played with those semantics already, so that's why I included Łukasiewicz. 3 axioms, very nice. Language is the same, so you can even nice exercise, proof with the same language. You have some axioms, proof which formulas you have to prove within the Łukasiewicz axiomatization to carry the proof I gave you. You can do it. So this is Łukasiewicz. Now, Hilbert and Ackermann, and that's why I was, it was before they decided to use another form of modus ponens. The language they use only disjunction and negation and axioms, and modus ponens is in that form, right? Because we know that implication, classical implication, we know that classical implication is logically equivalent, not A or B. So the modus ponens can be A, not A or B. So this is our modus ponens translated into the language which has disjunction. And again, you see, this is, you can call it modus ponens because of that expressibility of implication in terms of disjunction and negation, but that is only in classical logic. So that what they developed in 28, and they like that language, and they did, again, nice exercise. Take our proof, retranslate, and carry all the proof in that Hilbert Ackermann formalization. And now we have deduction theorem. Again, you have retranslated the deduction theorem. Hilbert, he had, you see, he wanted to have the full language, so he gave a full language and the full axiom. You see, there are axioms for conjunction and disjunction, you see, so you have 14 axioms. And also axiom, Hilbert proposed those 14 axioms and was accepted for axioms defining intuitionistic logic, and obtain classical adding A or not A. So that is very famous. So that was Hilbert show, that those axioms are not enough for completeness of classical logic, but they are intuitionistic logic. And then people agree that, yes, there were no semantics for intuitionistic logic, that, yes, we will call that intuitionistic logic. And then Kleene, I put Kleene because we were playing with three-valued Kleene logic. So Kleene had 10 axioms, and again, at that time, they were 10 axioms for intuitionistic logic, and added one more axiom to obtain the classical logic. And Rashowa-Sikorski, 1950, which had another type of proof, which are called algebraic proof. They have the same 11 and 12 axiom, A or not A, A or not A for classical logic. So, and the last, almost last, the shortest axiomatization, because, you know, people have 12 axioms, 20 axioms, 3 axioms, 8 axioms. So there's natural problem. Which would be the shortest axiomatization? And Meredith in 53 show, yes, you have this language and you have one axiom and modus ponens. And prove so we can have our implication negation with one axiom. So what I gave you wasn't the shortest axiom. I gave you 3 axioms because they were very comfortable to prove deduction theorem and completeness theorem. And then we can, as I also told you that, and we know that we can have one connective, classical connective, which would define all other connectives, and these are called arrows. One was Schaffer arrow, and the other Łukasiewicz, and up arrow and down arrow. And Nicot in 1917, he just did it. You know, he didn't prove completeness, but he said that that we can have an axiom, which one axiom, and that is a form of modus ponens. So it's another. This is another axiomatization which uses one axiom and the language with only one connective. And you can, for example, we prove chapter 3 that the language, the full language classical is equivalent to the language with up arrow or low arrow. And so, and then I give you more exercises, which I'm not going to talk, we already talked enough, that very nice exercises on monotonicity property, of completeness, definition of formal proof, and of course, you know, when I give exercises, I make the solutions. so with beautiful solutions. So this is very nice exercise, because those exercises are not difficult, but they sort of help you to understand those notions. What does it mean consequence? What does it mean completeness, and so on? So you have also the exercises which are solved in the book. And also at the end of the chapter, there's a lot of problems which are not very difficult, which you can use as a training ground. Okay, thank you. That's us chapter 5. We will do chapter 6 next time.